Here's a question I might ask you. So pause the video and spend a minute or a few minutes answering this question, and then come back and see what I write. Okay, here's my list. Compare it to yours. I think I captured everything in 8 points. So the review was week 1, motion, weeks 2, 3, 4, forces, weeks 5 and 6, energy 7 and 8, week 9, week 10, week 11 and 12, and week 13. You can see all that in Moodle. It's good just to step back and take a look at the big picture, the overview of what we covered over the course of the semester. Next item in terms of overview is the equation sheet. The equation sheet really is a good summary and an essential resource, but you have to know what's there. You really should go through step by step every equation and make sure there's no equation on here that you don't recognize or you're familiar with. So the math review equations are all here. I think you know all these. Here are kinematics equations. And remember, we spent a lot of time talking about these. These are our definitions. And these are the 4 working equations that we use for solving problems. These equations are derived from the definitions, but they are our working equations. And so if you're asked to explain the difference between average and instantaneous velocity, you start with the equations, right? And you should know, for example, in the acceleration equation and the velocity equation, what this limit is delta t goes to 0. It's a calculus concept, and it's important to understand and be able to explain that. The instantaneous velocity has to be a small distance and a small time to be close to the value of an instantaneous velocity. And the calculus derivative is really just defined by this expression. In math, you use a slightly different expression. So this is an important concept. We don't calculate derivatives, but the concept of the derivative and being able to define instantaneous velocity is important. Here are vector equations, finding components from magnitude and direction, and finding magnitude and direction from components. These are equations that we used all semester and will use next semester. The 3D kinematics equations we didn't really use. They're just a generalization of these equations. And remember, we can write these equations in x and y. When we do projectile motion, we change all the x's to y's. So we don't write them twice. And here's Newton's second law. Here are all our force equations for friction, the force of gravity, the spring force, and, right, assignment 13, the force for the universal gravitational force, right? We do Fg equals mg, that's good on the surface of the Earth, but this is good anywhere in the universe. Then our work energy equations, right? Weeks 7 and 8. Then our momentum equations. And the integral, I use the integral, but because you're going to see it. But remember, the definition of impulse is the force times the time, and it's equal to delta p. That's the impulse momentum theorem. There's our very simplified definition of the law of conservation of momentum, but you know how that writes out. You have to do that when you did the problems. M1, V1 initial, etc., etc. That's not all there. Feel free to write notes on this equation sheet. There's nothing inappropriate about making notes to yourself on your equation sheet. Here's week 10, our rotational kinematics, the definitions, the working equations, right? These are similar to these. And these are our conversion equations. We use them when we want to change from rotational velocity to a tangential velocity, etc. And the last page of the equation sheet, which for some reason I can't get to copy clearly, but there are your torque equations, your rotational inertia equations, parallel axis theorem you can follow on your own equation sheet, and rotational kinetic energy and angular momentum we didn't get to, so we didn't talk about that, or fluids, but we did do this, gravitation and gravity. And then remember, you have these for your prefixes and some of your units conversion are here on the equation sheet. So all of that. So essay questions can come in a variety of forms, and one thing that I often do is give you a term like torque, and I'll say, oh, explain in equations, words, diagrams, and examples the concept of torque. In that format, you would write down these two equations, you would explain them in words, and you would refer to diagrams, since you can't draw them, diagrams in the assignment itself, and give examples. Another form would be, I can give you an equation, I can write down this equation and say, okay, explain this equation. And so there's several levels in which you want to, if I give you an equation and ask you to explain it, words, diagrams, and examples, let's try it. Let's just do it with this equation. So here, I give you this equation. The question is, explain this equation in words, diagrams, and examples. And I'll give you one prompt. The first thing you want to do is identify every symbol in the equation, and then explain what the equation is, what it's used for, and give some examples of how it would be used. So start with this equation, take some notes, and then come back and listen to me and see what you missed or how well you did. Okay, here we go. There's various levels of completion you could answer this at, but at the very first level, this is torque, Greek letter tau, and this is the definition of torque. And it's a way of calculating torque, and it also tells us what determines, in any situation, what determines the torque. There are three factors that determine the torque in any situation. So T represents torque, R is a vector that goes from the axis to the point of application of the force. F is the force that's applied, causing the torque. And the cross product is simply a vector cross product notation for the product of the magnitude of R times the magnitude of F times the sine of the angle between them. So I explain the R and the F, and notice, don't just say a radius, that's wrong. R is a vector from the axis to the point of application of the force. F is the applied force. Theta, don't just say it's an angle, that's not good enough. It's what angle? It's the angle between these two vectors. Okay, so that's just the entry level. I've told you that this is the definition. I've identified all the terms. We can use this to calculate torque, and it tells us the three things upon which torque depends: the distance from where the force is applied to the axis, the magnitude of the force, and the sine of the angle. Okay, so what are the examples? So since you can't draw a picture, you could refer to a diagram from the exam itself, like a wrench, or you could, or if necessary, you could describe a wrench. Just say, imagine a wrench where one force is applied close to the front of the wrench and the other force is applied far away from the wrench. And imagine a force where you pushed or pulled along the axis of the wrench. So by example, you can explain how the maximum torque is going to come. The bigger the force, the bigger the torque, the bigger the distance from the axis, the bigger the torque, and the closer the angle is to 90 degrees, the bigger the torque, and the maximum torque comes from an angle of 90 degrees. Okay, so that's a fairly long answer. Okay, now try this equation. Explain this equation. Same way. Okay, notice the difference. This equation was a definition, and it told us what torque depended on. This equation is a relationship. It's very different. It's quite a different kind of equation. This is the relationship between the net torque acting on a body, the rotational inertia or moment of inertia of the body, and the acceleration. It's a relationship between three quantities. This should be identified as being sigma, the summation system. This should be identified as rotational inertia or moment of inertia, which itself we could ask about later. And this is angular acceleration. Remember, say rotational or angular acceleration. You might mention that this is the rotational analog of F equals ma. That's a useful observation and connection. It's also useful to now take this equation after you have identified all the symbols and rewrite it into two new forms. So it is informative or useful to look at the rearrangement, two rearrangements to this equation. And one is alpha is the ratio of the net torque divided by the rotational inertia. So again, a relationship. The amount of angular acceleration you're going to get for any angular acceleration is going to depend on the net torque, right? The net torque acting and the rotational inertia. So more torque, more acceleration, more inertia, less acceleration. It's also useful to rewrite it this way, that rotational inertia of an object is the ratio of the torque to the acceleration. And remember, in lab, we use this relationship by measuring torque and angular acceleration to get the rotational inertia. That was method 1 that we used in lab. And so you can cite examples from lab. If, like the red and the blue rod, it took a big torque to get the same acceleration on the blue rod, which had more inertia. Or the red rod, which had less inertia, the same amount of torque would produce a greater acceleration. So this ratio captures the notion of resistance to angular acceleration. And that's how you should think about rotational torque. So if this relationship is a definition of anything, it could be used as a definition of rotational inertia, which is, in words, resistance to angular acceleration. Okay, 3 more equations. This is why I want you to review the equation sheet. Can you do the same thing we did here with this equation? Can you identify all the symbols? Can you explain the relationship? Can you give examples? We talked about this earlier. There's a lot to say about this, right? This V is for instantaneous velocity. The instantaneous velocity is, what is this? This is the average velocity, where the average velocity is calculated over a smaller and smaller time interval. And as t approaches 0, as the denominator approaches 0, this ratio of delta x to delta t approaches a limit, which is defined in calculus as the derivative of x with respect to t. And that, in fact, is the instantaneous velocity. And it's worth mentioning that it's the slope of the graph of x versus t. So there's quite a bit to say about that. And then, obviously, you would want to give an example that distinguishes between average and instantaneous velocity and why it's important to get an instantaneous velocity to take a short time interval. And obviously it would be a good idea to refer to examples from the lab where we use the photo gate to do this. So that's integrating everything you learned into explaining this one equation. Okay, this last one that showed up in the last week, the gravitational force between any two masses, point masses really, right? When you're talking about the Earth and the Moon, they're tiny points of mass. And so this is for point masses. You know that from the assignment. And so the force of gravity between any two point mass objects is the product of the mass of both objects divided by the distance between their centers squared, right? When we measured to the satellite to the Earth, you didn't measure to the surface of the Earth. You measured all the way to the center. And G is the universal gravitational constant. It's just a constant of nature, and you might mention that it's very small. And that's why gravitational force is insignificant unless the mass of at least one of the objects is important. And the final thing, if you want it to be really complete, would be talk about this 1 over r squared relationship, which, remember, we also talked about. It signals an inverse square law where the force gets weaker as 1 over the distance squared. So if you go twice as far away from the center of the Earth, the gravitational force is going to be 4 times weaker. And this holds true for any point mass, like a light bulb emitting light, or a radioactive sample emitting radiation, or a point microphone emitting sound. This is a very common relationship in the physical world because of the three-dimensional nature of our world. And so discussion of the inverse square law is another possible question I could ask you on the exam. So give some thought to that. Obviously, the whole exam is not going to be essay questions, so there'll definitely be some MOPs, so you want to review the assignments. Go back to the old assignments, and the answers are there. You can re-answer the questions, cover up the answers, and pick the ones that you want to do for practice, and definitely practice on the MOPs. Quizzes are like condensed forms of the assignment. Maybe that's the best place to start, and then go to the assignments. And the labs should be reviewed as well. There were a lot of Moodle questions about the labs, and so you might want to review what you did, especially in the more recent labs since the midterm, the energy, momentum, and rotational motion, torque, rotational inertia labs. Those are all useful areas. So just go in and practice doing the things you're able to do and be ready to answer similar questions on the exam. Okay, I don't think I have anything else to say. Let me know if you have any questions.